Ça y est, c'est fini. Ouais. Ah. There is a low frequency. Voilà.
Ouais, mais là, on t'entend plus du tout.
Sinon, je vais prendre l'autre. Ok. Je vais prendre l'autre. Il n'y avait pas vraiment. Okay, so I'm going to speak about tour splitting algorithm for vehicle routing problems. So at the beginning, Caroline and Philippe asked me to give a talk at this conference, and I proposed this one, which is my one of my favorite subjects. And then I realized that it was a conference on integrated problems. So in fact, it's not really in the topic, but never mind, never mind. I hope it will be interesting and useful for you. So I don't guarantee that I will show you all the slides. So anyway, you will have access to the presentation after the conference. So don't worry, you will have the slides in PDF. So I'm going to speak, in fact, about a family of heuristics and metaheuristics for vehicle routing problems. So, for those who are not specialists, I'm going to recall briefly what a vehicle routing problem is. And then I will show you a brief history of route first, cluster second methods. Then the basic splitting procedure, which is reused in more complicated algorithms. And we will see an application to constructive heuristics and another one to a metaheuristic. And if I have time, we will see how to handle more complicated constraints in other vehicle routing problems. So vehicle routing problems, or VRPs in short, is an important research area. So it started in operation research by a paper by Danzig and Ramser in 1959. So it's not recent, and it's a research domain with an exponential growth. I stopped in 2013, but there were already more than 3,000 papers in Scopus for the period 2007-2013. So these problems are, of course, important applications in logistics, in distribution, but not only. And also, as Gilbert Laporte underlined, they are important laboratory problems. Gilbert said, the study of the VRP has given rise to major developments in the fields of exact algorithms and heuristics, in particular sophisticated mathematical programming approaches and powerful metaheuristics for the VRP have been put forward in recent years. So one of these problems is the TSP, the traveling salesman problem, but also more complicated problems with several vehicles, and it is true to say that, for instance, several metaheuristics like on-colony optimizations, they have been developed first on vehicle routing problem. So in the SECL, I will take as examples the capacitated VRP and the CARP. So the capacitated VRP or CVRP, it's really a classical academic problem in vehicle routing. So it's defined on a complete undirected graph with n+1 nodes. The nodes include one depot, node 0 usually, with identical vehicles of capacity big Q. And the other nodes are customers with known demands QI for one product, for instance. And we give for each edge traversal cost Cij. And the goal is to find a set of routes of minimum total cost to visit all customers. So the problem is NP-hard because it contains the traveling salesman problem as a particular case. So exact method can solve optimally problems with up to 200 customers, but of course many real instances are bigger, so heuristics are still required. Here is a typical solution for Euclidean instances. The customers corresponds to points in the Euclidean plane, and it is a classical instance CMT6 with 50 customers. So you see the depot is more or less in the middle, and the different routes it looks like a flower with its petals. And the capacitated recruiting problem is similar, but here the goal is to visit a subset of edges, of required edges, ij with demands qij. And we have a typical example is waste collection. So for instance, one edge ij can be a street segment, and the quantity qij can be an amount of waste to be collected. So again, the goal is to find a set of routes with minimum total length or total duration to visit all the required edges. And the current best method is BOD on Hernige. It can reach, well, it depends on the instances, but on average 100 edges. I know Angel is working on a new one, an ultimate metaheuristic for the an ultimate exact method. Sorry for the CARP, and we hope it will go further. So you know there are two strategies for vehicle routing heuristics. A VRP, it's a partitioning problem and a sequencing problem. Why you have two kinds of decision. You have to decide, in fact, which customers you are going to assign to each vehicle. So it's a partition of the set of customers. And then you have a problem of ordering or sequencing problem. You have to decide in which order you are going to supply the customers, if it's a distribution problem. So the professional dispatchers, instinctively, they build groups of nodes, one group per vehicle, and then they solve, they compute one route for each group. So in fact, they partition first, and then they find the order, an ordering in each group. So it gives a family of methods called cluster first, route seconds heuristics. And there is a second family, less known, sequence, where you sequence first. So they are called route first, cluster seconds heuristics. So in a first step, you relax vehicle capacity to solve a TSP, a traveling salesman problem. So you get a tour, a TSP tour, which covers all customers, so it's often called a giant tour, and then you cut it, you split it to satisfy capacity constraints. So these are two opposite approach, which are illustrated here. Here I have built groups of customers. The depot is in the middle. And then, beginning at the depot, I build a trip, a route for each group, and the vehicle at the end returns to the depot. But I could do the opposite. So route first, cluster second. I forget the capacity constraints, I build one giant tour, and then I split it to respect vehicle capacity. So I don't know if you are familiar with this domain, but the first group it's well known now. There is, for instance, a sweep heuristic published by Gillette and Miller, and the professional logisticians, they do that instinctively. So they divide the city into polygons, for instance, or big squares, and then they build separate trips in each polygon and in each square on a map of the city. So it's typically a cluster first, route second method. But in contrast, the second group, it has been cited, but only as a curiosity for a long time. And Laporte and Sommet in 2002, they said, we are not aware of any computational experience showing that route first, cluster second heuristics are competitive with other approaches. So my goal, of course, is to show you that the second group can give good results on various VRPs. So, in fact, with Philippe and Caroline, we noticed that the TSP tour, which is built in the first step, is not really used. So quite often we are given an ordering of customers, for instance, a priority list, and we want to split this list optimally, subject to the sequence, into feasible routes. So now we prefer to say, I prefer to say order first, split second methods. So a brief history. Bisley in 1983 showed that any TSP algorithm can be recycled for the CVRP using an optimal splitting procedure called split. I'm going to show it to you soon. But he gave no numerical evaluation, not at all. So it was a good old time where it was possible to publish without a heuristic, even without numerical results. It's more difficult now, I think. And Ulusoy in 1985, he adapted a split to a CARP with heterogeneous vehicles, and he gave one example on the drawing of one small graph. So it's funny to see that there are some theoretical results on worst deviations to the optimum. Altin-Kemmer and Gavish, for instance. So it's a CVRP with unit demand, so all the demands are equal to 1. So they show that if you compute an optimal TSP tour, and if you split it, the ratio between the cost of this heuristic and the optimal cost, it's bounded, it's a 2 minus 1 over big Q. So big Q is the capacity of vehicles. And Janssen in 1993, he found a similar result, but for the capacitated GRP. So the GRP, it's the general routing problem. It's like the TSP, but you can visit, you have a combination of required nodes to be visited, and required edges. So the capacitated GRP, it's the same, but with capacitated vehicles. So it includes the CVRP and the CARP as a special case. And Ryan, in fact, it was in the PhD thesis of Schoring. I have no idea about the pronunciation of this name. They studied one petal. So one petals are routes where the customers are in ascending or descending order of a polar angle relative to the depot. So you see, this is a petal, this is a petal. So for instance, if your vehicle goes anti-clockwise, and if it comes back clockwise, it is not one petal. So they noted that you can compute solutions which are made of one petals very easily by splitting a giant tour. So you have the depot, a set of customers. So you compute a giant tour visiting the the customers in ascending order of a polar angle, taking the depot as origin, and then you split it. So it does not solve the CVRP to optimality, but you obtain the best possible solution with one petals. Unfortunately, these solutions, in practice, they are not very good compared to the optimal solution of the CVRP. So in 2001, with Philippe Lacombe and Weber Hamdan Sherif, we designed mimetic algorithm, so hybrid genetic algorithm for the CVRP and the CARP. And our good idea was to code the solutions. The chromosomes are giant tours, in fact, and the evaluation procedure to evaluate one child solution, or to evaluate one chromosome, we apply the splitting procedures. And at that time, the best methods were taboo search method, and we obtained the first genetic algorithm able to compete. Then, since that time, split procedures have been designed for a lot of other routing problem, and several types of metaheuristics, and we can see that in fact the best method today are mimetic algorithm, so not pure GAs, because the pure GAs without local search, they are not aggressive enough for combinatorial optimization. But on one side you have a genetic algorithm and ILS based on giant tours, and the main competitor is ALNS, adaptive large neighborhood search. So it's funny that the technique was applied first in metaheuristics for the VRP, and only later Volk and with Nassim Al-Abadi and Mohamed Reghiwi, we evaluated, in fact, simple heuristics based on giant tours to see, yeah, finally we have never evaluated simple heuristics to see if they are competitive with the existing ones for the CVRP and the CARP. So it came later. And then GA is a return. We had a fantastic PhD student, Thibaut Vidal, and he designed a hybrid GA, which is currently the best metaheuristics for 26 kinds of vehicle routing problem, and it's also an algorithm where the chromosomes are encoded as the giant tours. Plus, he uses, of course, a lot of other tricks, but his algorithm is very efficient. So if you want an overview, I put, well, it's a nice paper, not because I am of the author, but it's good for PhD students because it's not only a survey, but we recall the algorithm and we give numerical examples and algorithms. And then we comment the paper. But we found already 74 papers. So a lot of papers were written in our group, but we found papers from Germany, Spain, Brazil, Japan, China. So now a lot of people use this method. So what is the principle? So I show you on an example first. You consider a giant tour. Here it's a giant tour with 5 nodes, 1, 2, 3, 4, 5. So it can be obtained by any TSP heuristic or exact method. We don't care because anyway our need is to split it. So how to cut optimally this giant tour. So the demands are close to each node, you know, and in this example we assume a capacity Q equal to 10. So the idea is to build one auxiliary graph in which there is one dummy node, one fictitious node, 0 at the beginning, and then each node in this auxiliary graph corresponds to one customer. And each arc in this auxiliary graph models a possible trip which can be extracted from the giant tour. So you have first all the arcs here, you see, between two consecutive nodes. So this arc, in fact, corresponds to a trip visiting customer 1 only. And the value you put here, it is the total length of the trip. And you see here, a route visiting only customer 1 costs 20 kilometers, for instance, and 20 kilometers to come back, so 40, okay? Here, customer 2, it's a trip visiting only customer 2. It would cost 25 and 25 to come back, okay? Then you put the arcs for the trips of two customers. So this arc models the trip visiting customer 1 and 2. And you see that cost would be 20 plus 10 plus 25, so 55, okay? So you put, in fact, all the subsequences of the giant tours, which can give, which correspond to a feasible trip, they are included in as arcs in the auxiliary graph. So why don't we have 1, 2, 3? It's because of the capacity constraints. A trip visiting 1, 2, and 3, you see the total load would be 5. Plus 4, and remember, vehicle capacity is equal to 10. And then once you have this auxiliary graph, you compute a shortest path from the first node to the last node. So you can use Bellman's algorithm for a cyclic graph. The graph has no circuits by construction. And you obtain the shortest path in red, and the total cost is 205. So what does it mean? It means the optimal splitting, you build one trip with customer 1 and 2, then one trip with customer 3, and 1/3 trip with customer 4 and 5. So it corresponds to this solution, and you can check that even on the original graph, that the total cost is really 205. So it's optimal, the splitting is optimal, but of course you don't solve optimally the CVRP. But this giant tour is split optimally. But of course we don't know which giant tour is going to give, after splitting, an optimal CVRP solution. That's the problem. So Bellman's algorithm is the one which is used for project management. For instance, I put here 2 iterations. So here the label of the node is 0, and you initialize all the other labels to plus infinity. And first iteration, you examine, you inspect the node, you process the node from left to right. So first iteration, we can put a label on node 1 and node 2. Then we inspect the second node. We look at its successors, and each time we can decrease the label of the destination node, we do it. So of course it's incomplete. You have to finish the algorithm, but if you do that, you will find the 205. So you see, it's very easy. So in fact, more formally, the auxiliary graph it has n plus 1 nodes numbered from 0, and a feasible route, so it's TI-TJ, it's not TI plus 1, it's TI-TJ, it's modeled by arc I minus 1 J. So this is visible here. For instance, you see the subsequence T1, T2 corresponds to the arc 0, 2. Here it is a subsequence 2, 3, 4. It corresponds to the arc 1, 4. Well, this is conceptual. You are not obliged to. At the beginning, we really, in the first implementation, we really built the auxiliary graph in the programs. So we constructed this graph, and then we computed the shortest path, but there is it's not mandatory. So it's possible to compute the labels directly using this algorithm. In fact, there are two loops. One loop with I, in fact, it browses the index of the first node of each subsequence, and then j varies from I to n, and it is the end of the current subsequence. So provided this subsequence ti, tj is feasible, you can compute the cost of this route. You compute the sum of the arc cost, and then you update directly the label vj of the destination node in the auxiliary graph, but you don't need actually to build the auxiliary graph. So we call that the implicit auxiliary graph. So it consumes less memory, and it's also faster, of course. So, as I said, the giant tour can be built using any TSP algorithm, but it's not necessary to use an optimal TSP algorithm, because it would be too easy. If you compute an optimal TSP solution and then you split it, you don't necessarily obtain an optimal solution for your vehicle routing problem. So good tours, they work as well. So you can use any heuristic to compute the giant tour. And if you split it, in general, you obtain fairly good solutions. Also, we can see that this algorithm, basically, it's equivalent to enumerating all the subsequence ti, tj, and there are n squared subsequence. So this is the complexity of the algorithm. So split runs in O of n squared. So n is the number of customers. We can be more precise. If there are b nodes per route, per feasible routes on average, it means that there are, in the auxiliary graph, b outgoing node per node. For each node you have b arcs which leave this node. So it means in total you have nb arcs, and the complexity of Bellman's algorithm is linear in the number of arcs. So it means the algorithm, in fact, it runs in O of nb. So in general it's better than n2, because especially if the capacity of the vehicle is small, you don't have trips with almost n nodes. You have small trips, for instance, with 2, 3, or 4 customers. In that case, the second complexity is much better. So for the CARP, it is the same. In that case, T is the giant tour. It's a list of required edges instead of a list of customers. But you have to choose a direction. So if it is a two-way street, in the giant tour you have to select one traversal direction for each edge. And these edges are connected implicitly by shortest path. So I said at the beginning that metaheuristics based on split, they are known since 2001, and the evaluation and constructive heuristics is more recent. This is one reference, for instance. And our idea at that time was to use very simple heuristics to build giant tours, and then randomized version to generate as many giant tours as we wish. Then each tour is cut using different splitting procedure, the one we saw on improved versions. And of course the best solution is returned at the end. So it's the principle is very simple. So it's difficult to be simpler. We use the nearest neighbor heuristic, so you know it for the TSP. Beginning at the depot, you build an emerging trip, and at each iteration, you add the closest customer. So this is the deterministic version. So in the deterministic version, here at this iteration, we would add this customer, because visibly it is closest to I. Okay. So now to generate many different giant tour, we randomize it. So it's very easy. In fact, of adding the closest node, you build a restricted candidate list. For instance, the k nearest neighbors. Here the k equal to 3. It's a parameter. You choose it, and you draw the next customer at random among the k nearest one. And you do this at each iteration. So provided you don't reinitialize the random number generator, if you call a second time the same heuristic, you will obtain a different tour each time. And you split all these tours and you return the best solution. So we tried also improve the version. It is a flower version. In fact, at each iteration, you build two groups of customers, the customers not yet visited. So L1, the customers which decrease the distance to the depot, and L2, the customers which increase the distance to the depot. And in fact, if the current load of the vehicle is a multiple of vehicle capacity between a multiple of vehicle capacity and the same total load plus 50%, in fact, you draw a customer in L2, otherwise you draw the next customer in L1. So it's a simple trick. In fact, it means that when you will split, when the vehicle will be more than 50% full, it will be time to get closer to the depot. It will be time to go back, in fact. So this kind of giant tour, when you split it, the giant tour in general is close to the depot when it is cut by the splitting procedure. So the travel cost to go back to the depot and to leave the depot for the next trip is reduced. So it's a simple trick. As examples of improved version, you can do a split with shifts. So in the normal, so here it's just a subsequence of a giant tour, a subsequence T2, T3, T4. So usually the cost that we put in the auxiliary graph is the cost. It is the cost for this trip. So 25 plus 30 plus 25 plus 40 to come back. But now we could say, okay, it is the cost if we leave the depot and if we visit the subsequent in this order. But we could do a circular shift, or if you prefer, it corresponds to a best insertion of the depot. So in the classical trip, in the classical split, the cost of this subsequence is 120. But if you decide to begin with customer T3, then you visit T4, then you come back circularly to visit T2. You obtain a cost of 100. And if you start with T4 and then you visit T2 and T3, you obtain again 120. So it's possible to build an auxiliary graph in which for each arc, remember each arc represents one trip, we put in fact the cost which corresponds to the best insertion of the depot. Of course, somewhere with the graph you have to remember where the depot has been inserted for each arc, but it's not a problem. So it gives better results on average. And for the CARP, in fact it was invented by Wildermans in the thesis of Wildermans. I remember Angel asked me once a question about that because he had a paper for review. So here it is the CARP. So T2, T3, T4, in fact it can be a subsequence of edges, streets with waste to be collected. So your giant tour is like this. Here I draw a second layer, and inv of T2, it is the inverse of T2. So it is the street T2, but traversed in the other direction. Okay, so the second layer corresponds to the inverse, so the other traversal, the other direction of the arcs in the first layer. And the idea here, it's so to compute the cost of the subsequence is very easy. The upper subsequence, you just make the cost of the edges. But now I want to select at the same time the best traversal directions. Okay. So for this, you just build a small graph like this, and at the end of each edge, you put the cost to go to the beginning, to the first node of the next layer, vertical layer of edges. So if you compute here, if you keep the initial directions of edge, the cost for subsequence T2, T3, T4 is 80. But in fact here, the optimal, by using again Bellman's algorithm, we can see that the shortest path, it is you traverse T2 backwards, so you invert the initial direction of T2, then you visit T3, and then the inverse of T4, and you have a cost of 64. So we call that split with flips. So in fact, you can do a splitting algorithm in which you have a giant tour with edges, and simultaneously you cut it into routes satisfying vehicle capacities, and at the same time you select the optimal direction of each edge. So it's possible to combine the two. It's more complicated to combine the shifts with the flips. So we made a comparison with two classical constructive heuristics for the CARP, which are well known, path scanning and augment merge. Why on 23 small instances, they are not big, but at that time we had the optimal solutions. It was possible for us to evaluate the distance to the optimum. So what we do, we randomly 20 giant tours, so either with this randomized version, NN, nearest neighbor, or this one, NNF, nearest neighbor flower version, and then we cut using the basic split, or the split with shifts, the split with flips, or the split with both, so with shifts and flips. So the running times are absolutely negligible, less than 10 milliseconds on a 3 gigahertz PC. Here is what we obtain. So the curves here, we put the minimum gap and the maximum gap. So the two curves here is nearest neighbor plus split. In fact, it is the best version. It is split with shifts and flip. And the two lower curves, it is the randomized heuristic nearest neighbor flower followed by a split. So you see that the results are much better. So here you have the results of the classical heuristic, path scanning, and augment merge, and then you see that if you use NNF, you have a smaller difference between the minimum and maximum cost. So it means that the heuristics in that case are more robust, more stable. So we see we are below 5% if we use a split with shifts and flips, and we retrieve 8 optima out of 23, which is good because anyway it's not an exact method. These are just heuristics, and we try to generate with the same heuristic to push instead of 20 giant tours to generate 10,000 giant tours, and we have an average optimality gap of less than 1%, and we find 16 optima out of 23. And the running time, even for 10,000 giant tours, is only 0.15 seconds. So it's very. So you see, it's extremely simple, but it works. So now. Sorry. So now, how to use these splitting procedures in metaheuristics? So the general principle is to search the space of giant tours, and then the giant tours, of course, will be split to get a solution for the VRP studied. So it can be any kind of VRP. It can be the classical capacitated VRP or another one with different constraints. And we apply immediately local search to improve solution, because you know, especially vehicle routing, in vehicle routing, the metaheuristics without local search, like the pure GA or the pure on-colony optimization, they are not good enough. It's combinatorial optimization problems are really hard, and you need intensification with local search, using local search. So all the efficient metaheuristics for vehicle routing problems, they include a local search. Okay. And then once you have a solution, to go back to the space of giant tours, you concatenate the sequence of customers of each route to rebuild, to deduce a new giant tours. So how to generate new giant tours? You can use constructive heuristics at the beginning to initialize the algorithm. If you have a genetic algorithm, you can use crossover operators. You can cross two giant tours to produce new ones. In on-colony optimization, you can build giant tour by using one ant, depositing pheromone along a path, and this path can give a giant tour. And you can use also mutation in genetic algorithm or perturbation in iterated local search, but it's the same. It's a kind of perturbation applied to one giant tour. And also, if you have VRP heuristics, which builds a complete solution, you can concatenate the routes one by one. You remove the depot, in fact, and you concatenate the customers of each route, and it gives you a new giant tour. So the situation can be depicted like this. On the left, you have the search space explored by the metaheuristics, so the set of giant tours. On the right, the set of a complete solution for your VRP problem. And the metaheuristics will navigate, is going to navigate between the two spaces. So from one giant tour, you can give a VRP solution using a split. And to go back, you use concat, the procedure that I call concat. So the advantages and the drawbacks, there is no loss of information. Why? Because we saw that split cuts each giant tour optimally, subject to the sequence. And there exists at least one optimal giant tour. So this is an important remark. Why is there an optimal giant tour? Consider an optimal solution. Assume that you know the optimal solution of your VRP. If you concatenate its routes, you are going to obtain a giant tour, and if you give this giant tour to split, it will find again the optimal solution. So it means that there exists somewhere what I call an optimal giant tour. I mean a giant tour which, after splitting, is going to give an optimal solution for your VRP. So you see there is no loss of information in searching the space of giant tours. So another advantage is that, of course, the space of giant tours is much smaller than the set of complete solutions, because you don't have the different ways of partitioning each giant tours into routes. Also, if you do a GA based on this principle, you can recycle, you can reuse all the crossovers designed for the TSP. And for the giant tours, you have no capacity violation is possible, so you don't need a repair procedures. In the first genetic algorithm for vehicle routing problems, some crossovers, they gave routes violating vehicle capacity, so it required repair procedures to transfer some customers to the other routes to reduce to correct the overload in the faulty route. Okay. Also, it was a remark by Federico della Croce. He said, it's funny, your split plus concat, they act like a large neighborhood move. So it's a very... I mean, if you have made a local search for the VRP, for instance, you transfer one customer to another route. So it can be improving or not improving. But on a giant tour, if you take one customer, you move it in the giant tour, and then if you split, the results can be completely different, because the limits between the successive routes can be completely shift forward or backward. So if you do split on plus concat on a giant tour, especially with a local search in between, it gives it's a powerful transformation. So the drawbacks, some problems may need a tricky split procedures. We saw the basic one, but sometimes they are more complicated. And there is, of course, the additional running time of split. To move from the left to the right, each time you have to run split, but as we saw, O of n squared, if you use a basic implementation, a simple implementation, you are in O of n squared, so it's fast enough in practice. So what we tried, in fact, a multi-start ILS. Philippe calls a grasp ILS, but that's the same, multi-start ILS. So ILS, it's powerful and simple metaheuristics. So there is a survey, a book chapter by Lorenzo. So, in fact, you improve solution using perturbation on local search. You have only 3 components: one greedy heuristic, one constructive heuristic, to build a first solution S. Immediately you apply local search, and then you do a certain number of iterations, and each iteration you take a copy of the current solution S prime, you run your local search, and if the cost of S prime improves S, you move to the new solution. Otherwise, you see there is no update. You stay on S, and you take S again, and you do a perturbation, local search, and so on. So you see, even the first solution here, it's a local optimum. So you run the heuristic and then the local search. And so this method generates a sequence of local optima with decreasing costs using only perturbation on local search. So why does it work? Glover, well, Glover is more or less philosophy sometimes. But yeah, it's an empirical principle called the proximality principle. He observed using intensive testing that in metaheuristics or for a lot of combinatorial optimization problem, local optima are often close to each other and they are grouped in clusters. So it's a fruitful principle when you are at the current local optimal to do little jumps, so perturbation plus local search, to try to reach the neighboring local optima. And the perturbation is very easy. It's similar to the mutation of genetic algorithm. For instance, you swap 2 customers at random in the current solution. But some tuning is required in this metaheuristic. So if the perturbation is too weak, the search stays in the attraction basin of the current best solution, and if the perturbation is too strong, the successive iterations are completely independent, like in a grasp, and it's the same. It's not very efficient. Also, the perturbation, you should not use a move which is used in the local search, because the local search will repair immediately the effect of the perturbation. So if you use a two-up move as a perturbation operator, don't use it in the local search. So here it's an example. Caroline will recognize it, I think. This one. You see, B0, it is the combinatorial space is like this. You have like a craters on the moon. In the middle, you have the deepest point, which is the local optimum, and you have other points. So these are the solutions. If you apply a local search, you will converge to the local optimum of this group of solutions. So it is called an attraction basin, a basin of attraction. So here I have a current solution S0, cos 120. I apply a first perturbation. I reach this one. You see the perturbation is not strong enough because the local search improves the solution, and I come back, I return to my initial solution. Okay. Then I try a second perturbation, which is better because I reach another attraction basin, and the local search goes to the local optimum, which is 125. Unfortunately, 125 is not better than 120. So I stay on this solution. I apply a third perturbation, and here I obtain a solution, and after a local search, I find this one with a cost of 113. So as it is better than my initial solution, I accept it. So now the current solution is here. Okay. So then I do a fourth perturbation, but not strong enough. So after the local search, I go back to this solution, and then a fifth perturbation, and this time after the local search, I jump to another attraction basin, and I found a new best solution, 100 with cost 110. So you see the principle. No? So how to improve? I like this character set. You know it. I discovered it recently. It was not in Word. It is the Consolas character set. It is a set of characters which is used by Visual C++. And in the past, it was not in Word and in PowerPoint. And now they added this character set to Word and PowerPoint. So you can, for instance, if you copy your Visual C++ code in Word, automatically it uses the Consolas character set, and exactly like in Visual C++. So this is the ILS, the multi-start ILS. In fact, the basic ILS is here, you see. But I add an external loop to do a restart. Well, at the beginning it is one start, it's not a restart. So there is a global best solution as a star, and then I do restart, and each restart is in fact one ILS. So I generate one initial solution, I improve it, and then there is the ILS loop. And at the end of each ILS, if I have updated the global best solution S star, I update it. So of course, this time, you see the difference here. I had a deterministic heuristic. But here, of course, if you use a deterministic heuristics, you will find not always the same result, but you don't have enough diversification. So the initial, the heuristic here must be randomized. So at each restart, you are going to generate a different initial solution. So it's an easy way to improve a basic ILS. So the one that we try for the VRP is an MS ILS with a giant tour. So it's almost the same. The differences are in red. Here we improve S by local search, and we concat its trips to obtain one giant tour, T. And in fact, the mutations are done on the giant tour. So in the ILS loop is here. I take a copy of the current giant tour, T prime, instead of taking a copy of the current solution. I split it. I split T prime to obtain a CVRP solution S prime. Then I apply the local search to the CVRP solution. And at the end of the loop, if I update the current solution of the ILS, I update it, and I concatenate its roots to obtain a new giant tour. So maybe it's not visible on this algorithm, but in fact the principle it is this. We have a giant tour here. The perturbation is applied to obtain a giant tour T prime. You split it, you obtain a CVRP solution S prime. You execute the local search, you obtain an improved solution S prime. You concatenate its trips to obtain a new giant tour. So in fact, the metaheuristics execute this cycle. So there is a cyclic alternation between the giant tours and the CVRP solutions. So the components are very simple. The heuristic to provide the initial solution is the famous merge heuristics of Clark and Wright. So the possible mergers, it's a heuristic in which you begin with back and forth routes containing to one customer only, and you merge them 2 by 2 to reduce the total cost. So to randomize it, the possible mergers of 2 routes, they are sorted in decreasing order of savings, and you inspect the mergers one by one, and the current merger is executed, but with a probability smaller than 1, and it's enough to randomize the heuristic. For the perturbation, we used a little trick. The perturbation, we perform k random exchanges of customers in the giant tour, and but the perturbation is adaptive. So at the beginning, we do a minimum number of exchanges, only 1. So k min is equal to 1. And at each iteration, each time we cannot improve the current best solution, we increase k progressively, but without exceeding k max equal to 4. So 4 exchanges. On the other hand, each time S is improved, k is reset to its minimum value. So it means that the strength of the perturbation, the number of exchanges, varies from 1 to 4. So as long if at each iteration you improve, it means that your perturbation is strong enough, so you will have k equal to 1. And when the metaheuristic has difficulties, suddenly it is difficult for it to find a new best solution. Then the strength of the perturbation will be improved progressively, and as soon as it is no longer necessary, you can reset the number of exchanges to its minimum number. The local search is quite standard. We use standard moves. We replace 2 edges by 2 others. We relocate a string of up to 3 customers. We exchange 2 strips of up to 3 customers. So these are classical moves. Implementation of the moves, they can be applied to 1 or 2 routes. The strings of customers which are moved, they can be inverted when they are reinserted in the destination route. And it is a first improvement metaheuristic, so at each iteration we don't search for the best improving move. As soon as we find an improving move, we execute it, and we move to the resulting solution. We also use some tricks called sequential local search, proposed by Ernisch. Very difficult to implement. And we made a test. So at that time, now there is a better algorithm by Thibaut Vidal. But Thibaut Vidal prepared his PhD here in UTT, and it was a co-tutela with Montreal. So we use 14 classical instances with 50 to almost 200 customers. And at that time, there were three best solutions, three metaheuristics with a deviation smaller than 0.3% to best known solution, with only one run. It's important because if you cheat, if you do a lot of runs with a randomized algorithm, maybe you can improve the results, but after 10 days of computations, it's cheating, I think. So there is this one of Mester and Brazy, active guided evolutionary strategy, bone root. So at the beginning, I discussed with Tarantilis. In fact, he speaks French. I say, why do you say bone root? Bone, it's a bone in English. C'est un os. And he say, no, it's a game of words. It's bone root. Have a nice trip. In fact, it is really a French name. And CEPAS and the mimetic algorithm with giant tours already 2004, but the MSILS is more aggressive. And you see the results, the deviation to the best known solution input average deviation. So the algorithm of Mester and Brazy, it's still the best, but the ILS is better than bone root, CEPAS, and the others. And moreover, it is also the fastest heuristics. You see here all the running times are scaled for 2.8 gigahertz PC, and you see that okay, it is not as good as Aegis, but it is 10 times faster. And Aegis is also very complicated. Mester and Brazy, they load the instance, they do a lot of statistics on the instances to identify clusters and so on, and they tune they run some heuristics to tune the parameters before launching the remainder of their heuristics. So it's very complicated. I think they have 13 parameters and a lot of components, while as you saw, the ILS is very simple. Anyway, Thibaut Vidal, he has generalized this approach, but he still uses giant tour, and anyway, it's now the best. The current best metaheuristics for many classical vehicle routing problems is a metaheuristics based on giant tours. So I put here, you will find these papers anyway in the paper I cited at the beginning, in Transportation Research Part C, order first, split second methods for vehicle routing problems, but you see there are already a lot for VRP with time windows, two echelon location routing problem, periodic VRP, heterogeneous split VRP, split delivery VRP, and you have also arc routing problems, capacitated arc routing problem, mixed CARP, periodic CARP, and so on. So it's effective. So I will just show you. I will not finish completely the slides. Anyway, you will have them. So you will be able to read them before going to bed in the evening. But before, for some people, it gives nightmares. But for some others, if you have difficulties to split, it can be also very efficient. You can fall asleep immediately. So this is the algorithm of the basic split. So in fact, we inspect all subsequence of the giant tour, Ti, Tj. So there is one loop for the beginning, the first index, I, and the last index, j. So j begins at I, of course, because j must be after I. So you have first to test if the route is feasible, otherwise you discard it, and then you compute the route cost, and then you update the label of node j, in fact, in the auxiliary graph. So, in fact, a lot of things, a lot of constraints can be handled in the two steps in red. So, what we have seen, it is a CVRP. So, the route is feasible. Here, you just check that the total load, the total demand of these customers does not exceed vehicle capacity. Otherwise, you ignore this subsequence, okay? But now there is a distance constraint VRP where you have a maximum trip length, so a maximum working time L. In that case, you would add a second test here saying if the duration of this route exceeds the maximum working time of the driver, big L, you ignore it. For the multi-depot VRP, it's more tricky. I don't know. Well, in fact, for each, you have a set of depots, and in fact, for each subsequence of customers, you just compute the best depot. So it is the depot which minimizes the cost to go from this depot to the first customers and to come back from the last customers to the depot. So you will say, it increases the complexity because I'm obliged to make a loop to compute depot D. No, in fact, the values of D, they can be pre-computed in a matrix at the beginning. You can build a matrix subscripted by I and J, and in which Dij is the best depot to be used for a subsequence beginning at index I and ending at index j. So you compute that only once at the beginning. And here we have the two red steps which are affected. For the VRP with time windows, in the feasibility test, you discard the sequences which violate time windows. And for the root cost, if your goal is to minimize the total time, you have to add waiting times. In the VRP with time windows, usually when it is forbidden to arrive at a customer after the closing time, so after its time windows, but it's allowed to arrive before. But in that case, you are obliged to wait. If it's a shop, a store, you are obliged to wait until the opening of the store. Vehicle fleet mix problem. In that case, you have P vehicle types, but they are not limited. The number of vehicles is not limited. So it's the problem when you want to build regular trips, and at the same time you want to buy the vehicles. So typically, you have different vehicle type. Each type T, it has a capacity QT and a fixed cost FT. It can be the purchase cost or rental cost. So feasibility test, of course, all the trips which are bigger than the biggest vehicle capacity, you can ignore them. And to the R cost, so you have, in fact, the cost of the route, but you have to add the cost of the vehicle. And as the number of vehicles of each type is not limited, you can take, in fact, always the cheapest type with enough capacity for the subsequent, and so on. Okay. So I put other example. I'm going to stop here. So usually, some people, they relax feasibility constraints, so they use a penalty. Thibaut Vidal, for instance, he accepts vehicle capacity violation. So he puts in the auxiliary graph routes which are infeasible up to twice the maximum vehicle capacity. But of course, he's obliged to add a penalty in the local search afterwards to reduce these capacity violations, because at the end, the final solution, we don't want capacity violations. So sometimes you need different shortest path algorithm, but the complexity in general is okay. It stays polynomial. And to be frank, so in the paper, order first, split second method, we give numerical examples. The difficult case, the most difficult case, is when the routes, they share limited resources. When the constraints concern each individual route, it's very easy. to modify the basic split, but here is one example where you have an heterogeneous fixed fleet. So you have different vehicle capacities, but with a different number of vehicles, a fixed number of vehicles for each type. So in that case, split must select one of the vehicles for each arc on the shortest path. So for each route in the splitting process, it must select one vehicle. But of course, the path must use at least 80 vehicles for each type T, where 80 is the number of vehicles available. So it gives the NPR resource constraint shortest path problem, but hopefully there are dynamic programming methods, algorithm with shortest path algorithm with multiple labels per node. So for instance, for this problem with the P vehicle type, we can solve it split in O of M and P. So M is number of arcs in the auxiliary graph, N number of customers, and P. So for fixed P, I like this kind of cheating. For fixed P, it's polynomial. But of course, if P equal 2 or 3, it's okay, but once a Brazilian student sent me an email, yeah, I tested your algorithm, and even to execute one split, it takes 60 seconds. I said, how many vehicle types do you have? He said, 18. I said, yeah, maybe not as the power 18. Okay. So I hope now you have I hope you feel that this principle, or the first second principle, is general non-flexible. A lot of people now use it because, as I said, we found 4 years ago 74 references. So spontaneously we receive papers now saying, "Hey, I read your survey, and we also publish one paper. So record it for the next version of the paper." There are some theoretical results. The current-based metaheuristic, anyway, it's based on this principle. The splitting can be done in polynomial time in most cases, but the current limit, to be honest, when the underlying shortest path problem is no longer polynomial, and is the case for the heterogeneous fixed split VRP. But anyway, we have at least pseudo-polynomial complexity algorithm. And there are 2 interesting research directions. If you are young and full of energy, not like me, I am old now. So there are the design of faster splitting algorithm for hard cases. For instance, there are in the last 4 years, I saw several papers on large resource constraint shortest path problems. So they invented a lot of tricks to solve. So it could be used for the heterogeneous split VRP, for instance. And also, you saw that we alternate between 2 search spaces, the search of giant tour and the search of complete solutions, but in a blind way. And I think a better exploitation of this alternation is probably possible. For instance, the metaheuristics could work for a given number of iterations in the set of giant tours, and we could find a clever criteria to say, now it's time to apply split and to move to search a bit in the space of a complete solution, and then also to go back, when to go back to the set of giant tours. I'm convinced we could find a more intelligent criteria. That's all. Thank you for your attention.
Thank you, Christian. Do you have any question on the presentation? Yes. So, sorry, I removed.
Hi, thank you for your presentation. It was very interesting. I was wondering if you have compared this split idea with the cluster first and then the Turing. Is that, I mean, is split more efficient or the other one? Or
giant tour at random, and if you split it, usually it's not better than more complicated heuristics like Clark and Wright, or there is one of Gillett and Miller and Fisher and Jacquemart, which are cluster first, root second. But it's so fast, split is generating one giant tour is so fast that usually what we do, we randomize the giant tour construction and we do 20 iterations. So you generate 20 giant tours at random, you split them and you return the best solution, and in that case it's better than Gillett and Miller. But it's a question of time, and then it's up to you. So you can increase the number of giant tours, and you obtain in general better solutions, but the running time is proportional to the number of giant tours, because each time you run a split. But it's very easy, yes, to outperform the classical heuristics.
Go ahead. On the same idea, so this split procedure is very dependent on the first TSP tour, like the big tour, right? So have you tested if there is kind of an inflection point in the construction of the big tour? I mean, applying the split procedure along, you improve the big tour to see if kind of there is like an inflection point?
No. It's funny, at the beginning I tried to use an optimal TSP algorithm to solve the TSP optimally, and you split, but it's a different problem. The CVRPs, it would be magical, it would be too easy to solve the TSP optimally, to split it and in polynomial time, and then to obtain an optimal CVRP solution. And surprisingly, you use any greedy heuristics like nearest neighbor to build the giant tour, and it works as well. It's incredible. So then if you use the nearest neighbor heuristics to generate a lot of giant tours, after splitting, the tours in general are good, are very good. So then you have just to increase the number of giant tours to increase your chance of finding the optimum solution. And in the example that I gave for the CARP is the case. If we go to 10,000 giant tours, okay, it's a lot, but it was 0.15 seconds. We solve a majority of instances to optimality. Of course, we know that because there is an exact algorithm. It's a heuristic, so in advance we cannot guess if we are going to get an optimal solution, but it works. But it's an interesting question. It would be interesting to guess in advance the kind of giant tours which are going to give an optimal solution after splitting, of course. Yeah, for sure, they give a bad VRP solution. Yes.
I mean, it's getting worse. So I was wondering if there is
Yeah. We try, but we found nothing significant. Okay. Thank you.
Any other question?
Thank you for your presentation. You said that the split algorithm is optimal when provided we give it the optimal, more or less, greatest path, right? I mean, the split procedure is optimal. So are there any studies on the microscopical study of what is the what is particular about a longer path that can give us the optimal VRP when we split it?
No, it's in relation with your question. For sure, when you have any giantor, you know how to split it optimally, subject to the order of this giantor. So, of course, the question is, what is the giantor which is going to give the best VRP solution after splitting? So this is the role of the metaheuristic, precisely. The role of the metaheuristic is to search the space of a giantor. So using perturbation, when we have a good giantor, the ILS, for instance, is going to apply a small perturbation to the giantor to generate giantor which are very close in solution space, and we expect that we of course, in addition, we add a local search. So after splitting, immediately we run a local search to improve as much as possible the result, the solution obtained by split. Okay, so up to now, we use a metaheuristic to try to find better giantors. No, but it's a good research subject. I count on you, all these young people to. No, but there are nice results to find, I think, yeah.
Other question?
So, can you adapt this method to solve the combined pickup and delivery vehicle routing problem? The simultaneously pickup and delivery?
Nubia Velasco, there is a paper that we signed with Nubia Velasco at the Universidad de los Andes in Bogota, Colombia, and it was a classical pickup and delivery problem to transport passengers to offshore petrol platforms in Colombia, in the Caribbean Sea. In Colombia, but it works. So it's a genetic algorithm with a splitting procedure. So of course, when you split, you must keep in each route the pickup point and the delivery points, because it's one consistency rule of the pickup and delivery problem. Yeah. So in fact, you generate all the subsequences, but provided they contain the pickup and delivery point of each request, but it works. But for more complex, after that it can be difficult if you have additional constraints. The splitting procedure can be more complicated than this. But for the basic PDP, it works. It's done. It's done.
One other question, maybe? Yeah.
Just a comment, maybe not for Christian, but for the PhD students. So you all dream of using the split algorithm from Christian's technique to adapt to your problem. But remember that there are years of research behind this. So even if he's telling you some tricks that he put in some papers, you don't have the whole truth. You just can't trust this guy up to the end.
Yeah, I'm a specialist of that. Quite often there are some tricks here. So, because I like to develop algorithm, complicated algorithm. So if one day you are unable to reproduce my results, just send me my email, and I will give you some hints to improve strongly the results. Priority lists or tricks like that.
So, Christian, just to thank you for your talk. I have a small present. Yep, sorry. That's for your talk and for you. And I just
Thank you very much.
And I just remember people who register for the project on split algorithm that it will just follow after the break, and it will be at the second floor in building M. So it's in M207. Yes. So bring your computer. We have all the branching things, but yes, and for people following us on internet, we just have a break of 20 minutes more or less, so we will be soon back here. See you.